Okay. So, any questions up till now? You got the shifting? Okay. Now our goal, before I continue, let's see why shifting does make sense. See, I'm trying to say that this thing I wrote here is same as this thing I wrote there, right? Are they really the same? Well, these two are just copied over here, so the only question is this thing same as the shifted one? Only way to test it out is to actually plug in the values and see what terms you get. So when n is 2, what's the very first thing that this produces? 2 times, 1 times, a2, x to what power? 0th power. What's the next one? 3. N becomes 3, so it's 3 times 2 times a3 x2 first power plus
4.
That's just one more. 4 times 3 times x a 4x squared. That's and then plus da da da. Okay. Now think about what this produces when n is 0. If n is 0, what do you get? 2 times 1 times a2 x to the 0th power. The same as this one, right? What's the next one? N becomes 1, right? 1 plus 2 is 3. 1 plus 1 is 2. 3 times 2 times a3 x to the first power. Exactly same as this one, right? So we do see that this thing produces exactly the same thing as this one. Right? The reason that this happens is because there is more than one way to express a given sum using the sigma notation. Right? And all we are doing is we are trying to write it in a different way so that it has x to the n rather than x to the n minus 2. That's all we are doing. Does that make sense? Okay. So that's the crucial part, the shifting. Okay, so now let's maybe since we lack the room, let me just copy this and then we'll continue. Okay, so we have so far sigma n equals to 0 to infinity n plus 2 n plus 1 a n plus 2 x to the n plus sigma n from 1 through infinity negative 3 a n a n x to the n plus sigma n from 0 to infinity a n x to the n. I just copied this. So let's just check that we didn't make any mistake in copying. I think everything is good. Okay, everything looks good. Okay, so I just copied it. Now what we need to do is to actually write out the sum. Okay. Yes.
I think you forgot the 2 in the last.
Yeah, 2a.
Oh yeah, thank you. 2. I forgot the 2. Thank you. All right. So now we have to go back to the actual summation. We actually have to write them out, and so I mean I wish we could just write all the sums and everything will be very clear. But then it's also very messy. Writing down all the sums all the time that's very very long and messy, and sometimes it's hard to find the pattern if you do that. Writing it this way will make it easier to find the pattern. Okay. Okay. So this is going to produce something. This is going to produce something. This is going to produce something. You can think of basically these as factories that produce items. Okay. So you have factory A, factory B, factory C, and in 8 a.m. all the workers go to the factory and start making stuff. Okay. You can think of that, right? Okay. And in the first hour, n equals to zeroth hour. In the 0th hour, the workers in factory B, they're lazy. They don't show up. Okay, so they don't produce anything. But at n equals to 0th hour, what's produced? This one produces a term. This one produces a term. This one doesn't, right? It only starts producing something starting from n equals to 1, right? So if you actually wrote out the sums, here's what's going to happen. When n is equal to 0, this one is going to produce 2 times 1 times a2x to the 0th power. This is not going to produce anything at all, right? And this one is going to produce 2a0x to the 0th power. How's that? Is that good? Yeah. 2a2. Just check that out. I'm right. Okay. This starts at n equals to 1, so that doesn't produce anything. Okay, but the other ones, the first factory and the third factory produces something. Then, starting at n equals to 1, they all produce something, right? So what do they produce? They produce 3 times 2 times a3x to the first power plus negative 3 times 1 times a1 x to the first power plus 2 times a1 times x to the first power, right? And the reason that we did the shifting was so that when we are doing this, when we actually explicitly write them out, we always get the like terms. See, these are like terms because they all have x to the first powers, right? So we can actually factor the x to the first power out and write it like this. How's that? Okay. So this is the line where you get for n equals to 0. This is the line that you get when n is equal to 1, and the clock just continues going, and the factory workers.
Why'd you skip that space for?
Huh? What?
Why'd you like? Yeah.
Oh, this one doesn't have it because at n equals to 0, this factory doesn't produce anything. It starts from 1, right? It doesn't start from 0. It starts from 1. Okay, and then the next one will have x squared in it, right? Now let's see if you can manage to tell me what you get. What do you get in the first factory? I factored out the x squared, just the coefficient. What?
4 times
4.
3, a4.
Okay, that's good. What about this one? Negative 3 times
4. I mean 3.
2.
2. N is 2 right now. 2 times a2. How about this one? Plus
2 a sub 2.
2a sub 2, right? X squared. That's for the case when n is equals to 2. Right? Is that right? Okay. Yeah. And then the clock keeps ticking, and the workers start working, and they just produce infinitely many terms. Okay. Now, what should all these equal to?
0.
Even this one, I should factor this. Okay. So I need all of these to equal to 0 because the right side has 0 in there. Okay. Which means this has to be 0. 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 All the coefficient must be 0. And that will give me infinitely many equations which you can solve, right? Okay, so let's see how that helps us. Now, in fact, you can rewrite what we have so far like the following. The first 2 terms are produced by these 2. But after that, it follows a pattern, right? Because all the factories start producing something, right? So let's see if we can go back to the sigma notation and write down what we just wrote in sigma notation. See, that's the trade-off of trying to become green, right? If you try to save the environment, it's hard, right? You work harder in order to save the environment. So because we're trying to use the sigma notation, you have to work more. And it's basically like this. We had 2 times 1 times a2x to the 0th power, which is just nothing. And then plus 2 times a0 to the x to the 0th power. This didn't produce anything. But after that, every one of them started producing items happily. So starting from n equals to 1 through infinity, here's what we have. We have n plus 2, n plus 1, an plus 2, and then minus 3n an plus 2 an, and then times x to the nth power. That's what's going to be, right? So if I just put this together, while factoring the x to the nth power out, this is all you're going to get. Is that right?
Mm-hmm.
Okay. Yes.
Where do the first two things come from?
Oh, those are the terms that's produced when n is equal to 0. We just had it right before when I raised it, right?
So that's work group A and C.
So yeah. It's a factoring 1 and factoring 3 each produce this one, that one. But after n equals to 0, starting from n equals to 1 to infinity, they all produce something, and now it fits in the pattern. Yes?
In the parentheses, could you change it to minus NAN? Because you have a minus 3 and a plus 2.
Oh, actually, that's what I was about to do. So let's simplify this. You have 2a2 plus a0 plus sigma n equals to 1 through infinity, n plus 2, n plus 1, an plus 2. Now these two can also be put together because that's an, right? So you have negative 3n plus 2.
Even with the n?
With an. No, negative 3n plus 2.
With that n, you.
Yeah, we need the n. You can't say negative 3 plus 2. It's negative 3n plus 2.
No, I'm saying you can combine that.
I mean, I can factor out the an because they are common factors. So I factor the an out, I get this, right? Yes.
Would you not distribute the n plus 2 to the n plus 1?
No, you don't want to do that. Okay. So I have this. Any other questions? Yes.
Wouldn't that be equals to parentheses a2 plus a0?
Oh, yeah, that's what I meant to do. Thank you. Okay. So that's what I get if I simplify. And then each one of them should be 0. So first I know that a2 plus a0 should be 0. And you want to say that a2 is negative a0. By the way, I should have mentioned this before. What is a0 according to this?
1.
A0, this actually means that a0 is 1. What does this mean? That means what is what?
A0 prime.
A1 is
Oh.
negative 1. That's what it is. I mean, that's only obvious after you write this out. See, if you write this out, that's a0 plus a1x and plus so and so, right? If you plug in 0 both sides, you get a1 equals to y of 0. Well, y of 0 is 1, so you get a0 equal to 1. Now here, n starts from 1, so the very first term that doesn't have x attached is 1 times a1. So y prime of 0 is 1 times a1, and solving for a1, you get a1 equals to negative 1. Now if you had a third order differential equation, you can have y double prime equals to some value. In that case, y double prime will correspond to 2 times a1, 2 times a2. So y double prime of 0 divided by 2 will be a2. So you can work this out, okay? So we already know the value of a0 and a1. So because I know that a0 is 1, I know that a2 is negative 1, okay? And that's pretty good because I know a0, a1, and a2 already, okay? Yes?
Wait, why'd you set that whole thing equal to 0?
Oh, because this entire thing has to equal to 0, right? For that to work, this has to be 0 and that has to be 0. Actually, that's the theorem in power series. For infinite polynomial to be always equal to 0 for all values of x, when you organize things in the powers of x to the n, all their coefficient must be 0. So that has to be 0, and that also has to be 0. Okay. Now, so we got a2 as negative 1, we got a0 as 1, and a1 as negative 1. So we already got 3 out of infinitely many. I guess that's still 0%. But it's good. We know three of them. Okay. Now we will try to solve this. I need this to be equal to 0, right? Equal to 0. So what does that mean? That means n plus 2, n plus 1, an plus 2 is, if I move to the other side, I get the negative of this, which gives you 3n minus 2 an, right? And then I can divide both sides by n plus 2, n plus 1, n plus 2, n plus 1, so that after canceling them out, I get an plus 2 equals to this. And this equation here is very convenient because for n equals to 1, what does this say? a1 times this thing, whatever that is, gives you a3, right? If you plug in n equals to 2, a2 times something is a4. Do you see that? So for n equals to 1, let's see what this says. If you set n equals to 1, for example, you get a3 is 3 times 1 minus 2 is 1. 1 plus 2 is 3. 1 plus 1 is 2. And a1. And what is a1? a1 is negative 1, so you get negative 1, 6 for a3. Okay? And then you can plug in n equals to 2 and do the same thing. And that way you can get a4 as something times a2, which again you will get something, right? So you see that when you set the coefficient of x to the n equal to 0 and solve for the a of the higher index, see this n and n plus 2, those are called indices. Yeah. So here's an index n plus 2. N plus 2 is bigger than n, right? So this one is the term with the higher index, bigger index. If you solve this equation for a of the bigger index, you get this equation which you can use over and over again to figure out all the coefficients after a0. Right? Once you have this, you can just use them over and over again. Okay? And therefore, this has a name. This is called the recurrence relation. So maybe I should delete this and say that this one here is called the recurrence relation. Okay. And using the recurrence relation, you can plug in n equals to start. This is value from n equals to 1, right? Because this starts from n equals to 1. So starting from n equals to 1, 1, 2, 3, 4, you just keep plugging in, and you're going to get all the values of an this way, just by using the recurrence relation. Okay, so we're pretty close to the actual answer. It's almost done now. It's almost done. So let's just write down what we know so far. I know that a0 is 1, a1 is negative 1, a2 is negative 1, a3 is negative 1/6. Okay, now what is a4? a4 is when you plug in 2 to this, 2 times 3 is 6, 6 minus 2 is 4, a2 over 4 times 3. So they cancel, and what is a2? That's negative 1, so it's still negative 1/3. Okay, and then I guess the sign will change now. What's a5? a5 is the case when n is 3, right? 3, so it's 3 times 3 is 9. 9 minus 2 is 7. a3. 3 plus 2 is 5. 3 plus 1 is 4. Right? So, and a3, it's negative 1/6, so it's like negative 7 over 20 times 6, 120. All right. Oh, I guess it's always negative after that. Okay, but that doesn't matter. We got up till a5, okay? And I guess we can do this forever, right? And figure out all the values of an. And since this is never going to end, let's just write it as a dot 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 notation. So the answer to this equation is the following: y must be 1 minus x squared minus 1/6 x cubed minus 1/3 x to the 4th minus 7/120 x to the 5th, and then I give up. This should be something. Who knows? It's some value. And that is the solution to this equation. You can plug in values if you need to. So for example, after solving this, if the question was, what is y of 0.1? What would you do? You plug in 0.1 here and get the answer. Yes?
On a test, how far down do you want us to go?
Yeah, so in the actual exam, often I will ask, find the first 5 non-zero terms, something like that. So you would stop somewhere here. Okay? Yeah. Or sometimes I would just ask, find the recurrence relation. So you stop at the recurrence relation. Sometimes that could be quite the question. Any other questions on this?